Perhaps we can get started. So the plan today is to somewhat finish the class on where we introduce the problem of semi-supervised learning and the approach that sometimes dubbed manifold regularization. And then to introduce the problem, we're going to switch gears and we're going to discuss the problem of multitask learning that we're going to start today and we're going to continue Wednesday. So first thing first, let's just try to summarize a little bit what we've been saying a week ago, I guess, a while ago. So let's try to remember what we said a week ago and fill in some of the gaps that were left and add a few remarks that we didn't discuss. So let me remind you, first of all, what is the setting of semi-supervised learning? It's more or less what the title says. So you get a bunch of data, okay, L of them, where you have labels, okay? And then you got a bunch of other data where you don't have labels. The typical scenario here is the idea is that while this one might be costly and it might be not too big, this typically is much cheaper. The kind of data is much cheaper to collect, and so U might be order of magnitudes bigger than L, okay? And the idea is that, to some extent, how knowledge of of unlabeled data could help predicting labeled data, okay? Clearly, in general, it might not be true. There might be a situation where there is not much help or not much improvement or improvement at all. One basic idea is that, of course, these data and these ones have to be related somehow, okay? And so from a modeling perspective, the idea is to assume, as we've done so far, that this data is coming from a distribution. I already split it in a conditional distribution for a fixed x over the possible outputs, and a marginal distribution, and distribution on the inputs, okay? The idea here is that the unlabeled data comes from the same input distribution. Now, here, if you want, there is a bit of a picture of what's going on with this modeling. We discussed already a bit, so this is already more or less giving you a highlight of what we discussed. There are at least a couple of features, okay? At least a couple of features of the input distribution, a couple of conditions under the input distribution that might suggest that knowledge of a lot of unlabeled data might help, okay? So let's think for a second that unlabeled data are so many that this that you essentially know the input distribution, okay? Just for the sake of simplicity. In this picture, you see what? You see the support of the input distribution, meaning the smallest set with measure 1, okay? The place where you pick points from. And here you see a couple of things. One is that I'm assuming that in this kind of setting, you typically assume that M, the support of distribution, is not the whole space of input, but has some further structure. And in this fantastic drawing here, you can see a couple of features, okay, that we discussed already a week ago. Do you remember what? We discussed essentially two properties of the input distribution that could be interesting while you try to make prediction of functions over that distribution. You can kind of read them out from this picture. So in this picture, this whole thing is the ambient space, if you want, is the X space, say RD, whereas this space here is this set, the support of the distribution, okay?
You have like some directions that don't matter to assume they lie in a lower dimension.
So one issue is that this set could be some kind of lower dimensional structure, okay? The intuition is exactly the one he just said, meaning some direction might not matter, okay? It's tricky here. Okay, this is the first observation. Here, what do we mean by low dimension? This might require some care, because this set, strictly speaking, well, now, of course, now 3D might be doing, but it might actually be of Euclidean dimension 3, okay? But the way I wrote it, you do feel that this is just a one-dimensional set, okay? And so to actually make this concept precise, one way to do it is to look at the notion of a manifold that we introduced a bit quickly last time, but it's basically the idea that you have a set that locally looks like RD, in which several of the common concepts you handle in RD, such as, for example, angles, volumes, gradients, and so on and so forth, can be defined in an analogous way, but in a way that is sensitive to the geometry of the space. Okay? So this is one idea. One intuition when you do this kind of stuff is that the input data is not really high dimensional, but is actually some kind of, is maybe not exactly, but so let's say in the simplest case, exactly lying on some lower dimensional structure. And of course here you can say, okay, I want to relax this. And typically the idea is that, well, these might not be exact, might be a rough approximation, meaning that the data are concentrated maybe not on a manifold, but close to a manifold, okay? So let me not do it, but you can try to, fatten this stuff a little bit, or assuming that you actually have tails. The data can be found anywhere, but the larger mass of the data will be close to a lower dimensional structure, okay? We actually discussed quite a bit a different perspective, well, related, but a little different, that is not directly related, connected to the idea of a lower dimensional structure, and is somewhat, imagine that this is a classification problem, okay? A binary classification problem. Which one do you think are the two classes? Well, it's quite obviously, your intuition said that this is one class and this is another class, okay? And what we discussed is by making this guess, we're basically assuming that the separating surface that tell me which class is which is not going to lie, is going to lie in a region with low density, okay, with low mass, where not much is going on, as opposed, for example, a decision like this that would go in and cut in regions where you really have a lot of masses. So if that's correct, it's fine, but it's going to be a very hard problem because a lot of things is close to the boundary. Okay, so these two intuitions are sometimes called the manifold assumption and the low density separation assumptions are two possible ways to formalize how and when knowledge of unlabeled data could yield improvement over knowledge of only a label set. Okay. Of course, now when I say formalize, I mean more like give an intuition, okay? It's not really a formalization. One step further would be to try to make this very precise mathematical and, for example, derive condition such as, okay, let's quantify what does it mean to have a low density separation. Let's put some properties of the manifold, and let's quantify, for example, in which regimes, depending on this assumption, it will be interesting to have unlabeled data. There might be a regime where, say, if you have enough labeled data, this won't help much, and regime where you don't have enough labeled data, and this would help a lot. So I would be very happy to be able to tell you what's enough, but as far as I know, we don't really know these kind of results yet, okay? Not even qualitative statement that just tell me, if this manifold is such and such, then I have a regime where, if the labeled data are little, then unlabeled data is going to help a lot, or it always helps, or something like that. As far as I know, we don't have a good theory for this kind of stuff. The practitioner view here is that typically, when the number of labeled data points is small, okay, then unlabeled data typically kicks in and can give you a fairly big boost. If you have enough labeled data, then unlabeled data won't help you a lot, okay? And what is small and enough really depends on the applications. And so it's just an empirical observation. Okay, so this is the setup, our frame set of mind when we start playing with unlabeled data. And the idea is the usual. We would like to derive some kind of regularized technique. This is some empirical error depending only on the labeled data because we don't have labels for the other ones. And this one is some penalty, okay? The idea is that we somewhat would like to tailor the penalty so that it keeps into account the observation that we just made, the low dimensional observation and the low density region intuition. And if you remember, this is what we wrote. Why? So first of all, where the measure as higher mass, okay, you penalize more. What do you penalize? This one is not yet the Laplacian, it's just the gradient. Okay, it's like big changes of the function. Okay, you say if my function changes a lot, points that are very likely to be sampled. I don't like that. I would like a function that doesn't change a lot, where points are likely to be sampled. And here, basically, the introduction of manifold is hidden in these two symbols, and it's basically a technical aspect that will allow us to make sense of this procedure in a rigorous way. Okay? We're not going to want to indulge in this. We didn't even do it last week. To some extent, from the algorithmic point of view, this appears pretty quickly. Okay? But that's kind of there in the background. And jumping a bit ahead, what we saw is that, well, in practice, of course, you don't have access to this rho x, this input distribution, but you have unlabeled data. Okay? I call here capital M the sum of the labeled and unlabeled data. Okay? And here what you could do is to try to use all the input points, labeled and unlabeled, to define some quantity that doesn't depend on the labeled data that you can use as a regularizer. And the idea is that this is going to be a proxy to this. Okay? So let's fill in some of these gaps. First of all, one observation we made is that we can rewrite this using some form of Stokes' theorem as a quadratic form. You remember how? So what you can do is that you can actually take the inner product of f the Laplacian of f, and this is going to be the space, let me write it like this, where this is just the space of function, is just L2, the space of function from x to r, such that if you want f of x square the rho x is less than infinity. Okay? Okay? And notice that here I put x, but I could just put m. Okay? Because anyway, this space depends on the measure, so whatever happens outside of the measure is not really seen in this definition. Okay? It's technically is a space of equivalence classes that can do anything off the support of the measure. But we don't care much about these kind of details. Okay, this was the first step. This is the Laplace-Beltrami operator on the manifold. And for us at this point, it's just a rewriting of the main intuition, which is that we want to penalize big changes when there is a high density, or rather high probability. Okay, so do you remember what was this? So this is a matrix, is m by m. This is a vector, okay? The vector I'm going to write for you. So f bar is a vector of size m, and it is just a function evaluated in all the points, labeled and unlabeled. Okay? What was L? I heard Laplacian and kernel. So L is a matrix defined to be D minus W. The name is graph Laplacian. Okay? We're going to see why graph in a second. W is required to be a positive matrix, not a positive definite, okay? A positive matrix, meaning that each entry is 0 or greater than 0. And usually symmetric, okay? If we do care about viewing this as an approximation to this, we have some rule in the way we have to choose the weights. And one possible way, the simplest probably, not the simplest, but among the legal one, the simplest one, is to do something like this. Okay? That is choosing not only a symmetric and positive, but also positive definite function, which is the Gaussian kernel, which is a function that basically says that we are in somewhat zooming in distances that are small and zooming out distances that are big. Okay? And the zooming factor is this gamma ij, which is actually typically chosen to be a constant. Okay? So this is just a Gaussian. Now, if you view it like this, if you make this choice, okay, or an analogous choice, you can actually now view the data, the labeled and unlabeled data, as a graph. What's the graph? what are the vertices of the graph? Well, just going to be the points, okay? And then the edges are going to be weighted with this, okay? So what is the idea is that in the limit, okay, where this is small enough, okay, the graph would be, strictly speaking, fully connected. Every vertex will be connected to any other vertex, okay, through this equation. And the idea, though, is that in some sense, you're going to explore the geometry of the set by basically seeing that the weights are going to be very small when there is not much going on, okay? Think of this situation as, for example, a discretization of, well, I guess this one should be here, or for example, something like this. This is, you know, a kind of a dumbbell. Imagine, so this thing that I draw, this 8-shaped thing, is the true distribution of the data. So it's in 2 dimension. It's not a manifold, okay? It's really a 2-dimensional set, but it looks like this. This is the support of the input distribution. I don't have knowledge of it. What I have is that I can sample these points, okay? Point 1, point 2, point 3, point 4. And then I can put weights, okay? And here again, it's just is a lazy drawing, okay? In fact, this point should be connected. This point probably can be connected, and so on and so forth. But the idea here is that in some sense, even here, what you see is that you will have more edges in area where you have higher concentration, in a sense, okay? Because you have more points and you connect them all. And you will have an interplay between the geometry and the distribution. Okay, so this was W, and this is, in this sense, this can be as a kind of an adjacency matrix or a weight matrix associated to this graph. What is D? Do you remember? So D, anybody remembers? You basically take W and you just sum the row and you put it on the diagonal. So DII is just the sum over J of Wij. Okay? It's the degree of the graph. You sit on a vertex and you see how many weights go out and you sum them up. Yeah.
When you're putting the weight on the vertices, do you assume that there is an edge between each, or do you assume like a priority?
So the question is, when I put a weight over over an edge, I'm always assuming that that edge is actually existing and is there or not. If I write this equation the way I presented it, yes. Because basically by doing this, if this is the way I do it, I really take, this is the only thing you care about. And so everything will be connected to everything. And the intuition is that by choosing this, you're making it, some of the edges will almost not matter, right? Because they're very small. But strictly speaking, this will give me a fully connected graph. In practice, what people do is that they actually try to get sparse graphs, okay? And what I mean is by sparse graphs here, that non-fully connected graphs. So there are essentially 2 main techniques, 2 main constructions to do this. One is what is called the k-nearest neighbor graph, okay? What you do is that you sit on a vertex and you decide what is the connectivity of the vertex, how many other vertices this guy should see, okay? And then instead of just putting 1 or 0, whether I'm connected or not, on the one that you're connected to, you could choose something like this. Does that make sense? How many parameters do you have in this case? K and gamma, okay? You choose the connectivity, and the 2 are not unrelated, okay? But this just to remember, because this means that, for example, this guy typically will have 1 or more parameters. One of the issue we're going to see is that you end up having quite a few parameters to choose in a way for which you cannot really design maybe a convex procedure. The other way of building a graph, which is not fully connected, is what is called sometimes you basically use the idea of using an epsilon ball. So instead of choosing how many vertices each vertex should be connected to, you just consider the radius of the ball, So in the first case, you say k equals 3. So each guy should just see the first 3 nearest neighbor, and that's it. In the second case, you decide the radius of the ball. Well, okay, you choose a delta, and you say, if a point lies, so I sit on a vertex, I see what's delta away, and those points I do want to count, okay? And so for those, I'm going to use some weighting. If the points are outside, I ignore them, and the weight is going to be 0, okay? So this will be an equation where, we don't write it because I think it's a waste of time, but you would have this condition for points that are sufficiently close and 0 for everybody else, okay? In this way, you do get a graph which is not fully connected. Of course, the question arises of what are we doing at that point and how these different choices compare to each other. And one way to see it is to check how they relate to our original. Because we have the model and this is how we started from, we can go back and see how they affect the construction of this through Regularizer. Okay, and there are quite a few results on this that are somewhat beyond the scope of what we're doing here. Okay, so this is the matrix. Okay. This quantity, unlike this, can be computed once you have unlabeled data. Okay? You just go in, you build the graph in some way. The simplest case, you just build the kernel matrix, okay? And then you do this. Or you can, as we just discussed, try to be a bit smarter and make it a bit more sparse, having a sparse adjacency matrix. And then you can just use this equation. Okay? Now, the results we mentioned is that it can be proved a couple of things, okay? One that I think you have to prove is that this guy can be rewritten this way. We're gonna, maybe we will 1/2 here. There might be a constant. And so this is going to be useful in a second, okay? And it's just an exercise, and I think it's actually one of the exercises in the problem set. And then the result, which is actually not at all an exercise, and is actually not easy at all. Well, depends on, is to prove something like this, that as m, the number of unlabeled data goes to infinity, there are certain functions, okay, suitable function f, such that this actually takes place, okay? So this quadratic form does converge to this, okay? That's kind of a theorem that you would like to prove. You're discretizing and you want to be sure that how the discretization works. And a byproduct of a theorem like this, that it will give you at least some qualitative result that tells you how you should choose gamma, or maybe how you should choose gamma and say the delta or the k nearest neighbor parameter that you use to build the graph. At least, and typically what you will have is that this will tell you that, you have to choose a suitable function, say, I don't know, km, where k is the nearest neighbor, and gamma, where gamma is this weight inside of the Gaussian, in a suitable way, depending on the number of unlabeled data. Okay? So you have to change the way you construct. The intuition here is essentially that when you have few points, if a point is far away and isolated, probably you don't want to take care of it. But if you start to get a lot of data, then you have to be careful and be sure that you take into account everybody. Okay? Because this is really, you're sampling more and more. Yeah?
Is it up convex? In which cases is this point going to be convex?
We're going to see it in a second, always. Yeah, you're going to see it in a second. The question was when choosing this kind of stuff will give rise to convex optimization problem in the regularization. We're going to, this is what I want to do next.
There are no zero modes to the Laplacian plate.
No, there are, but I mean, they will not affect the convexity. You might have that the problem is not strongly convex, but is always convex, okay? And we're actually going to make it strongly convex in a second. Okay, so this theorem like this are, if you want, the backbone, theoretical backbone of manifold regularization in this Laplace-Beltrami / graph Laplacian perspective, and but are somewhat beyond what we want to present here. What we want to do is look a bit exactly what we mentioned right now. That is, okay, what kind of problems I have when I plug in this regularizer in this equation. Any questions about this? Does it make sense? Not yet, it's coming. Okay, so far again, unlabeled data, labeled plus unlabeled data, try to exploit the geometry of the input distribution, or rather its support, manifold assumption, low density assumption, design of what is sometimes called a measure-based regularizer or a manifold regularizer, and then a bit of thinking of how to approximate this on a finite set of unlabeled data, okay? But taking full advantage on all the unlabeled data. So you see here that here in this expression, you even see it just from the fact that you put Rm here, you use all labeled and unlabeled data, just the input points, okay? The introduction of the graph Laplacian, which is an object interesting in its own right, and we're going to try to comment a little bit more on this object, why there is a graph underlying the construction, different way to build the graph. And then, if you want, a couple of theoretical observation, one which is basically an exercise and one which is not, and is really, as I said, the backbone of manifold, of the manifold approach to semi-supervised learning. Okay, so the last bit we want to recall is, what about computations, okay? As we said, we're going to have, I'm going to specialize the discussion for the square loss, but many of the stuff, more or less everything I say is going to be true for any other loss function, okay? I'm going to point you, and here let's just write this. So this is the problem we want to solve. Is this enough? As somebody remember, last time we actually added another regularizer. Why would you think we might or might not want to add a regularizer?
Because this doesn't define a norm by itself.
So one question is, what he's saying is, it doesn't define a norm by itself. I guess slightly more generally, one could ask, okay, what is the hypothesis space I'm working on? Where do F, I would like to write here a minimum of F that belongs to somewhere, okay? Where? And on that somewhere, I would like to have a linear structure that I can use, hopefully, to do, well, let's say a linear structure and an inner product so that I can use all the concepts, so a Hilbert space structure, okay? And then a norm and so on and so forth. So you can ask yourself, what is a good space for that? So this is one comment. There is also another comment that somewhat suggests that perhaps it wouldn't be a bad idea to consider some further regularizer here. What happened in the moment in which we realize that we don't have perfect knowledge of the input distribution but only have unlabeled data? Well, we replace this guy with this guy. Now, true, I know that they converge, but in some sense you can be afraid of some form of unlabeled overfitting, okay? Or if you want more intuitively, instability. How much this varies depending on the labeled data, on the number of unlabeled data points you have available, okay? Because remember, whenever we write something like this, we would like this to be something that stabilizes the problem. But now you have, and it's even more clear if you view it like this, something that depends on the data, okay? And the moment you change the data, you can ask yourself, what changes? This is observation 2. So the first is, what is the hypothesis space and how do we define a linear / inner product structure on it? Observation 2 is, regularization has become data dependent here and potentially subject to some instability. There is yet a third point perhaps here to think about. you can ask yourself what you're doing off the manifold, okay? That guy only see the labeled data. What do you want to do where you don't have data, okay? You might have the distribution or not, you don't know, but you have to decide what you have to do there, okay? So one choice is, that is the one that had been proposed, is to actually consider this space to be a reproducing kernel Hilbert space, okay? And add here another penalty. This will become, if you want, this is the way one could think about it. This becomes the norm in the reproducing kernel Hilbert space for a fixed kernel. You can view it as an ambient regularizer, meaning that it regularizes everywhere, okay? It doesn't really care about where there is more, the distribution is more concentrated or not, whether the distribution is more concentrated or not. Whereas this you can think of some kind of intrinsic regularizer, meaning that it looks at the geometry of the input distribution, okay? Now, the reason why I want to introduce this regularizer is for all the reasons I just mentioned, okay? And probably you can find a few more. I think it's useful to remark that you have this algorithm has quite a few parameters, okay? How many you have? How many you see there? At least 4, okay? So you have the 2 regularization parameters that I wrote. Then you can probably write here a gamma, maybe a k. Well, there are too many k's here, so let me do the delta of the delta ball constructor, or any graph parameter, the one that will make the problem more or less, the graph more or less connected, okay? If you want a threshold on where I want to put the weights or not. Then there is this other regression parameter. Then there is this kernel, and this kernel is likely going to have its own parameter, okay? So first of all, you have quite a few parameters, and you can ask, okay, how should I choose them? What is the theory that tells me how they relate to each other? I guess it's even more complicated than that, because now you have, if you want, you have a kernel here, and another kernel here. And so, for example, you could ask, okay, but how do I choose this kernel and that kernel? Okay? Either a result that tells me which kernel are admissible in this kind of construction. And if I use a Gaussian kernel, how should I choose the sigma of this Gaussian kernel that I use to build the graph, and the sigma of this Gaussian kernel that you use to define the hypothesis space? Okay? And as far as I know, there is no answer for these questions. Okay? Theoretically, there is no answer. This is kind of an open. All these questions that I just mentioned are open as far as I know. What you do is that typically you view them as tuning parameter, okay? And you have some heuristical choice, okay? For example, what you see is that, well, here you're thinking of a function that varies a lot, okay? And you want to enforce its smoothness on the manifold. Clearly, if you take this one to be the linear kernel, you're restricting yourself to linear functions, okay? So there are some obvious choices of, say, the graphs and the kernel that seem somewhat counterintuitive. So typically, you put here a Gaussian kernel, you put here another Gaussian kernel, and then you do some tuning of the parameter, you look at some stability, you look at some cross-validation, you choose them. But now cross-validation becomes quite hard because you have 4 or 5 parameters to choose, okay? So you will see that this has been one of the issues in practice. I think with these algorithms, they do require quite a bit more tuning than our standard algorithm that we have 1 or 2 parameters, okay? If you want from a practitioner perspective, you still do cross-validation, but you now have 4 rather than 2 parameters. So that's the complicated part. Luckily, there is an easy part, okay, which is the one where literally we recycle what we've been doing in the first part of the course, because now you have just that equation, okay, and now I can ask you, okay, fine, what are the other computation that are entailed by that expression? How do you find the minimizer? What do you think? How do you find it? Everything looks pretty good. Everything looks smooth, okay? Everything looks at least convex. We have to minimize over a function space which is potentially infinite dimensional. It's function in Hilbert space. So the first thing we want to do is to try to see if we can reparameterize our space of functions in a way that is useful, okay? And what's the way we do it? We did it when you have kernels. Representer theorem. Okay. In general, the function space does not have a finite dimensional parameterization, but we're lucky enough that in certain situations, the problem we're looking at can actually be restricted to a finite dimensional space. Okay. And if you remember, what was the main, what was the saving grace here? What was that allowed us to restrict ourselves to a smaller space here? So the smaller space where all the function, let me call it f hat, that could be written as some kind of combination. So the standard representer theorem, say if I put lambda I equals 0, this just goes back to standard RKHS, and this would be the expression. You remember what was the main reason why we managed to prove this?
The fact that the loss function is invariant in the orthogonal subspace.
That's a fairly complicated way of saying it, and it's correct. So let's try to see just translate that without using the word orthogonal subspace. What he's saying is, the simplest way of saying that is this term does not depend. So in some sense, if you look at this function, okay, this term will only depend on things that look like this, because everything else will be 0. So the function that don't look like this will be 0 on this term, okay? So strictly speaking, this term will be exactly what it says, invariant to the space which is orthogonal to the space of function, okay? So again, in other terms, if you pick a function and then you just use it on a point, only this part will survive and everything else will be disappearing. And this term here will be only minimized if you just also throw away the orthogonal part, okay? So only these survive. So without making the proof, but just continuing the discussion, how do you think this result is going to modify, is going to change now that we add this term? Well, so he said we have two kernels, okay? What do you think? Somebody else shaking your head? How this result would change now that you have this? It's useful to see this equation. Look at this equation and plug it there, okay? And now redo the same reasoning. We recall that you derive this equation because this term doesn't depend on anything on the orthogonal. And then you have this term. Now you also have this term here that looks like this. So how do you think this is going to change?
We're going to change kernel.
Why you want to change kernel? Well, so my question is this going to remain unchanged?
Yes.
Okay.
I think that you have to add the x 1 to u, so that.
Well, it's here, right?
1 to n.
Here or here?
Now, the general expression of the solution is the form instead of 1 to n, 1 to m.
Okay. So these are two guesses, okay? So somebody's saying, no, you should keep it like that, okay? But then you should change the kernel. And the intuition, I guess, following that idea is, well, you can in some sense view this as a way to change the norm. And you can ask a legitimate question, which is, oh, can I rewrite this as just a standard problem, but with a new norm, okay? On a new kernel that might depend on both the labeled and unlabeled data. You can go this way, okay? And it's actually a good exercise. Try to see what you get. We're going to go a slightly different way, which is what he's suggesting. And it's the easiest one, the one you can derive without thinking too much about it, which is the one where the guess is that, in fact, the representer theorem itself is going to change a little bit. And it's going to be a semi-supervised representer theorem, where the expansion is going to be over kernels centered on both the labeled and unlabeled data. Okay? How would you prove this?
Because in the orthogonal complement of this subspace, f of xi is 0 and f of xj is 0. So
Yeah. So it's the same reasoning as before. The same reasoning for which before this guy was 0. Okay? Now you also have that this guy will be 0. Only this guy sees both the labeled and unlabeled data. Okay? So you will need this many. So anything that is not of this form will disappear when you apply it here or here. And yet we'll be left with this, and the best thing is to throw everything to 0. Okay? That make sense? You can prove it a bit more precisely, but this is the main intuition. All we are left with, so now we have this new unlabeled, semi-supervised extension of the representative theorem. What's left to do is just to look at what are the CIs. Okay? How do you do that? Well, there are 15 different ways of doing it. One way to do it is to just use simple linear algebra, is to just do the following. Okay? So this is easy. It's already written like that. So F bar is just, it's still written there, is just fx1, fxm, that is exactly the training set. So how can I write F bar? K? Yeah, so let me call K hat the kernel matrix. That is big M by M applied to the vector C, which is M by 1. Okay, I took the kernel matrix, the one defined by the kernel that I chose for the space, not the one for the graph Laplacian, and I build this M by M matrix. Okay, how much is the norm? So this is a norm of a function that looks like that. Okay, so how much is it? Is C transpose, if you want, just write it in a product notation, it's just like this, where this is Rm. Now, I know that this is the quantity that define F bar, so I can also go on and rewrite this a little bit. Okay, so F bar L hat F bar Rm is equal to what? Well, I just have to plug in this guy, and if you want writing it again with the inner product notation, I have Kc, L Kc, Rm. So you can already see how you're going to do linear algebra here. It's useful perhaps to rewrite this slightly differently. Okay, you can immediately plug this guy in here, but then you will have only so many labeled data points. Okay, so one way to do it is to just take, let me just do this. Okay, you do the following. This term is really in this vector are really in Rn, okay? But you're artificially somewhat going to write it in Rm so that you can just take everything in Rm and make derivatives. What is J? What do you think J should be?
0 when labeled.
So it's a diagonal matrix, okay? That is going to be the identity for the first L entries, and then it's going to be 0 everywhere else. So what this does is it selects just the first n entries, and here you have to decide what you want to put, okay? But the important thing is that the first L elements have to be the labeled data. The rest, it won't be seen by the algorithm, okay? But the default choice is to put there 0, okay? Just because. And now at this point, you can just take derivatives, set it equal to 0, see what you get. And you would have that essentially what you get is something like this. So I don't remember the exact form, so let me just, also here you might, both here and here, you might want to normalize by the number of points, okay? So it would probably be a m square here and an n there, but now I don't remember how it's going to look like, so let me just do it like this. It should get something like this, okay? So this first part is the usual regularizer, regularized least squares, okay? If you now add this lambda I different from 0, you get an extra term. And then more or less the algorithm is the same as before. It's just a linear the inversion of a linear matrix. Okay? Make sense? And of course, here I just gave you the computations for the square loss, just because that's why I chose it, because you can just do this one derivative. But as you can imagine, up to here, this is true for any loss function, okay? Because any loss function will only depend on the training points. And of course, also these computations are all going to be true for any loss function. It's just a moment where you want to write the loss function and just take derivatives, whatever you want to do, that the space of the loss function is going to enter. Okay? So by taking this perspective, you can go on and do Laplacian regularized least squares, Laplacian SVM, Laplacian logistic regression, and keep on going, and augment algorithm by introducing this new form of information, this new form of prior on the solution. Okay? And this somewhat conclude what we wanted to say about this algorithm. Okay? It is a bit of a longer recap, because this part we almost didn't have time to do it, and it was a week ago. Okay? So this is more or less it. Questions or comments? Otherwise, we try to move on a little bit. So one comment is that while we are taking here the point of view of semi-supervised learning and going a bit more in detail into this, a lot of the intuition, the ideas, and the concept that we introduced in this class can be somewhat recycled and reused to consider other kind of problems. Okay? Particularly, what you can see is that there is a whole approach based on exploiting the fact that the Laplace-Beltrami operator on a manifold, or rather the spectral properties, so the eigenvalues and eigenfunctions of the Laplace-Beltrami operator, carry information about the geometry of the set. Okay? For example, one can see that if you have a manifold, you can ask the question of how you can, cut the space in two, so that in some sense you get two big fat regions. Okay? And you cut in an area with very small size, in a very rough sense. In this sense, the idea is that this is a good cut, whereas say this one is a bad cut. Okay. And of course, here I'm a bit sloppy. How do you define size? How do you define fat? Okay. But there are a few ways of doing this, and the idea is the Laplace-Beltrami operator is the right object to ask this kind of question on a manifold. Is that if you now either want to discretize the manifold, or you just have a graph, not necessarily a discretization of a manifold, okay? Maybe, for example, a random graph. These days, especially when you study networks of various kind, one makes different kind of models. Instead of assuming that the graph is just a sampling of a manifold, you could just say that this is a random graph, okay? A Erdős-Rényi graph, and there are a bunch of different models. And those kind, in this kind of setting, you can still ask the question, okay, you give me a graph, try to cut the graph so that you get two components which have a lot of connection between them, but you cut them in an area with not much connection. Okay, these will be, say, two big groups. And of course, you can keep on going and say, okay, how can I go on and cut in more than once? Okay. Again, this is something that is very popular these days in the study of networks. It's sometimes called is the basic of the so-called spectral clustering algorithm, or max cut algorithm, which is used, for example, to do segmentation or to do clustering. There are a bunch of theoretical results that tells you, depending on different models on the graph, what you can know. There are extensions of this idea that consider general notions that are similar but more general to these Laplacians here, that carries higher order information. For example, whether your set has circles, cycles, or holes, or handles. So they give you higher order topological information about the set of points. Okay, and these in the last few years there have been a fairly lively field of research sometimes the word topological data analysis is a word attached to it. And if you want, this is kind of an analytic approach to this kind of question. Okay, you try to reduce the study of the topological and geometric property of a set to the study of function and matrices or operators defined on this function. Okay, so rather than study the set directly, you define functions on it and certain operators on it, and then you look at their spectral properties and you try to derive from these spectral properties property of a set. So this is kind of an analytic approach. Okay, there's also a whole other set of techniques that somewhat work more directly with the space itself. And this is just, again, this is, as we go into this slightly more recent direction of research, these are pointers to things that have been either open problems or active field of research in the last few years. And this is definitely one, so we're not going to talk about this at all, okay? But there has been a lot of research in a lot of different directions. Okay, so we want to close here this this little window over the world of exploiting or learning the geometry of the data. So what we've seen is how to exploit the geometry. What I pointed here is that more generally how to learn the geometry of the data. What we want to do next is to consider a completely different setting. It's similar to the semi-supervised setting in that it's another augmented scenario, okay? So semi-supervised learning is augmented by knowledge of unlabeled data. Multi-task learning is a setting which is also somewhat extending the standard setting, and this is the idea. I don't want this. So usually what you assume is that you have a training set like this of n points. And the idea is, and we call this review as a task, okay, as a task that we want to solve. And the idea here is that you don't have just one task, but you actually have many tasks, and you have data for all the tasks, okay? So rather than one training set, you now have a bunch of training sets. Potentially of different size. And capital T here is the total number of tasks, okay? And as you can imagine, at this level of general, and if you want here, I would have that for each of this, there is a distribution, okay? And at this level of generality, it can be very general, because each distribution could be on input spaces and output spaces that are different from each other. Okay? So in its full generality, this problem is super general. Okay. In most of our discussion, we're going to restrict ourselves to the case where these guys are equal for all the problems. Okay, the data space will be the same for all the problems. And oftentimes we make further assumptions. Okay, but let's stick to this for a second. Why do you think it could be interesting to consider this situation? Well, at this level, I guess the question is not well defined. So clearly, there are situations where we have more than one problem. Okay, so that clearly in that situation you want to consider this problem because you have more than one problem to solve. What is the basic idea underlying this class of problems? Well, what is the default approach? I give you, say, 10 problems, and what do? You take problem 1 and you solve it. Take problem 2 and you solve it. Okay, and it's fine. You could do that. So the basic idea here is that the gain would be in taking a more comprehensive approach where we try to solve not each problem individually and separately, but we try to solve the problem at once. Okay? And there are several situations where you can imagine this would be a good idea. Okay? And we just try to draw one. It's a simple toy situation. This is x and this is y. So it's just one dimension and one dimension. So imagine that you got two data sets, okay? It's just two tasks. I hope I draw it so that you can see it. So the first data set is the one above, okay? 3 points. Both of them are actually 3 points. For the first data set, you have the first 3 points. For the second data set, the second 3 points, okay? You go in and you solve the problem for this guy. What are you going to get? Probably, other things being equal, something very close to linear. Okay, something like this. It looks like that could be a good solution. It's a simple solution. If you look at this, what are you going to get? I don't know. Probably something that looks like this. Okay? Suppose that I tell you that I know that the two curves, those two curves look very different from each other, right? But suppose that I tell you that I do know that those two curves should look very similar to each other. And then you can tell, okay, what do you mean by similar? Okay, but I say similar and you got it, okay? Then we have to be precise if we want to get an algorithm. Then, say, in the limit case, assume that the two functions are just the same, okay? If they're just the same, okay, exactly the same data set, and I just happen to be dumb and I've split it in two, then you can put everything back together and well, let me see if I can find another color. And the idea is that hopefully you get something that perhaps looks like this. So it has to go up. Then it will go down. Then it will go up again, and then it will go down again. Maybe something like this. Okay? Roughly. No? This guy pulls our prediction up here. Okay? And this guy convinces yourself that definitely we have to go up again and down. Okay? This is, in a nutshell, the idea behind multitask learning. Okay? This, if you want, is the case where I take the data and I put them all together. Okay? And now I say, train this. Multitask learning is we've seen the two extreme scenario. We say the tasks have nothing to do with each other. Just do it separately. Okay? In the other case, we say the tasks are actually just one task, just solve one problem. What we want to do is to at least interpolate between these situations. Okay? Say, okay, find something which is going to be not all equal, not all independent. Okay? And then, of course, you can complicate it and say, okay, find something where you might have groups or tasks that are similar. Okay? Or find something where I have some other prior information on the way I want to couple the problems among each other. But the idea is, on all these problems, that in this scenario here, by assuming tasks to be not independent, you can do what is sometimes called in statistics borrowing strength. Okay? You have a problem that doesn't have a lot of data, and now you borrow strength from another problem that also doesn't have a lot of data, but complementary information. And then by fusing this information, you can now get better results. Okay? So similar to the unsupervised, so the semi-supervised learning, this is a case where you can think this to be very useful in extreme cases, for sure, where the data for each task is very small. Okay? And in that case, you can, in this case, in the example that I tried to draw on the board, the effect is, you can imagine, will be striking, right? This toy example is almost the same as some real data that, for example, I don't remember the details of the data, but it's something like people, I think, measuring something like iron concentration, some substance concentrated in their blood during the day, okay, to monitor how I guess you could do this, for example, for glucose measurement for diabetes, but more general for other stuff too. Okay, diabetes, I guess, is more precise, but people might have different habits, different eating habits, and so on and so forth. Or what you might have is just, some other. I guess diabetes is tricky, but there might be some other substances. I think the one I remember, I think it was iron, that usually basically go up and down depending on the time of the day, and all of us are pretty similar, so we usually have pretty similar shape. But some people make measurements in certain time of the day, some people another time of the day. You like to get a very sharp profile so that you can, for example, administer drugs or know what's going on. And the data that you see in this kind of situation look just like this, okay? And literally you have that people take like a few measurements per day, okay? And so you hope that by having exploited the complementary laziness of the people, or then you can get better results, okay? So in a nutshell, this is the idea, okay? And what we want to do is design an algorithm, okay? And the algorithm is going to be, well, rather than one function, is going to be an algorithm that has to estimate now t functions, okay? And we want to do regularization, and so we will want a regularizer that also will take into account all the function at once, okay? This is the rough idea where we want to go. Rather than having like some or t distinct problem, we want to have one problem which is joint over all of them, and we want to know what you want to do with the loss function, what you're going to do. So you're going to do the error term, or you're going to do the regularization term. The approach we're going to take is going to be naive on the loss term. Okay, one reasonable question is, can you design a nice joint loss function? I'm not going to discuss that at all. And actually, aware of little work in this direction. We're actually going to take the other perspective, which is we're going to basically we're just going to take the sum of the error here. Okay, where each one of these is okay. So for the error term, most of our discussion we're going to be naive. We're just going to take the sum of the error of each task independently. Okay. If you don't do anything smart on R, if supposedly, for example, you just fix an hypothesis space and you just minimize this, then the problem will decouple. Okay, there's nothing that couples one task and another task. If you take the derivative with respect to, say, f1, only the data corresponding to the first problem is going to stay, and everything else is going to disappear. Okay, so we need to be smart somewhere else, because here we have been extremely non-smart. So before actually, no, maybe not before, maybe afterwards. So before describing, so for today what I want to do is to try to introduce just a linear framework, okay? A simple framework where what we do is that we assume each function to be just a linear function. Okay, just a simple case where the input space is Rd, and we just want to look at linear functions. Okay, that's what we want to do for today, and we want to think a bit about that. Before, you can imagine that once we make that assumption, we can immediately do a bunch of things. Before going that, let's take a little parenthesis, and let's try to see that the moment we make an assumption that function look like this, okay, in fact, we can view essentially the problem of learning a matrix. Because here, now I don't have just one Wj, but now I have t Wjs, okay? And so what you could do is that you can just shove them all together into a matrix, which I guess we can write as a t by d matrix, okay? So is just a little parenthesis for a few minutes about, as you can imagine, once you take that perspective, we derive this from a multitask learning perspective, but you can imagine many situations where what you have is that you're basically saying, I have a matrix, okay? It's fixed, it's given, it's somewhere, but I cannot observe it. okay, I can observe it through some measurement process. So I have a matrix W, and I have some measurement process that give me some numbers, okay? And maybe this is affected by noise, okay? And I can have different number for the different task. So this would be the case where basically what I do is that I have some in my matrix, okay? And then I get some noisy measurements. The problem we just discussed, the problem multitask learning, can actually be seen exactly this way. We actually are going to, for now, restrict ourselves to the case where these measurements of the matrix have a special structure. They're just as the inner product, the Frobenius inner product of the matrix W times some measurement matrices, okay? And these measurement matrices are going to write them like this. This is just a matrix, okay? And I'm going to have, you know, let me make the simplifying example that all the, in that case, that all the tasks have the same size. In this case, that I have the measurements are going to be divided like this. Okay? So what I want to do now is just, you know, I could just now tell you, okay, so I can look at problem like this for these specific measurements. Okay, this is just a matrix learning problem where I want to learn the matrix W, which is fixed but unknown. It's observed through these measurements, possibly corrupted with noise. Okay? This is a problem that it's interesting in its own right. I wouldn't have to derive it from multitask. What we want to see now is that we can view multitask as one case. You know, we can just view the connection between the two. So first of all, what is the, just in case you don't remember, the Frobenius inner product of two matrices A and B is just a trace of, say, A transpose times B. Okay? Now, the question is, if I want to derive the connection between these two things, okay? So I basically want to write f of xij as w xij Frobenius. How should I choose the matrix X? Okay? Is the notation clear? This is just my usual, sorry, this is fj. This is my vector, okay, which is in Rd, is associated to this observation for this particular coordinate in the output space. This is the function associated to it. And I want to write this as a fixed matrix, okay, times some kind of measurement matrix. So the question is, everything here is given apart from this. So what I'm asking you, how should I choose this? So what you see is that if you pick this to be the outer product between the orthonormal basis in RT and just the vector that appears there, sorry, J. I changed my notation between J and T, and a small t from the notes to the board, so sometimes I make a mess. So pick this matrix to be just this one special matrix, okay? Each J tells you which element of the orthonormal basis. So this is an element in RT, okay? And then this is just that vector which is in Rd. Now, it's a simple exercise to verify that if you now plug this and use the definition of the Frobenius norm, what you get is exactly this expression. Okay? So you product between the jth column of the matrix, row of the matrix W, and this vector here. Okay? This is very easy to see. You literally just take that, plug it in the definition, this is what you get. So the first observation I wanted to make is we're going to restrict ourselves to the case where functions in the multitask learning are just linear functions. And before discussing how to exploit this and derive regularization, we want to talk about matrix learning a little bit. Okay? And just observe that this is just that can be seen as corresponding to a matrix learning problem. A special case where the matrix observation are done through linear measurements and where the measurements have this form. Okay, so the particular case of linear multitask learning can be seen as matrix learning with measurements that just look like this. Okay? We want to do this connection because we can introduce a couple of other problems that are now can be seen as special cases of multitask learning or the matrix learning problem. And so the algorithm we're going to introduce are going to work for all of them. Okay? So we want to introduce two more problems. Okay? One is, again, a special case of this. So we can describe here and then see the analogous there. And it's the special case which you might call multivariate regression. And this is the case where all the inputs are the same for all the tasks. Okay? So xij is equal to xi for all j. Okay? So if you want, at this point, it's perhaps more natural to read the training data by fixing each input, xi, and collecting all the outputs into a single vector. So what I mean is that now I can rewrite this training set, okay, in this specific case, as a training set xi. For each xi, I'm going to collect all his output. Okay? And let's also make the simplifying assumption that at this point, all the training data are the same, the cardinality, I mean. And so in this case, you can see this as an element in Rd, and this as an element of Rt. Okay? So in the special case where all the inputs are the same, it's very natural to just view this as an extension of supervised learning, where the input are vectors and the output are also vectors. So rather than thinking of, oh, I have multiple problems, of course the two things are very related. When you have data where the output, instead of being one number, you have many, you can think of that just as a vector problem, or you can view it as a collection of t scalar problems. And if you view it like that, you can just call them tasks. Okay, and view this as a special case. It's the special case where all the inputs are the same. This is one way of seeing it, okay? Of course, you can always see it as a vector where you make strange observation of the input, okay? And this in statistics, this actually has a huge literature in statistics, in geostatistics, where you try to discover properties typically of 2- or 3-dimensional surfaces based on samples. And so the problem is intrinsically like more than one dimension, typically low, but more. And is the whole literature called, well, not quite this linear setting, it's like the non-linear setting we're going to see on Wednesday, called Kriging and co-Kriging. And the two models are, I think, is called the general multitask-like model is called heterotropic. Heterotropic. No, I remember it was not skedastic. So this one is called the heterotropic model, and the other one is called the isotropic model. So the case where all the inputs are the same. As you will see, probably Wednesday, the case where all the inputs are the same, for example, imagine that you want to measure, say, the velocity field in the 3D world. Okay, you're going to have each positions, and then you have to measure a velocity. This is the classical case where you're going to be in this kind of scenarios. The input is going to be, you sit in a place, and you need 3 coordinates, tell me where I'm sitting, and then the vector is going to be, again, the few coordinates tell you the direction and length of a vector. Okay? So this is a case where it's very natural to view it this way. If you take a problem where you have people and they have their ratings for movies, telling I like it a lot, I don't like it, and then you see a bunch of features to describe me, okay? probably this is going to be more like this, okay? And each of us is going to be a different x, collection of x and y's. The x's, for example, could be the movies that I like, okay, in the past. And the yj could be, say, how much I liked a specific movie, okay? Things like this. So these, of course, just correspond to the case where here, rather than having this kind of measurements, you have just like this, okay? The inputs are the same for everybody, but it's clearly just the same. So this is not a very particularly interesting case. In this framework, the third, so we can take, say, the heterotropic, the isotropic case, or we can also consider the pure matrix completion problem, okay? What is the problem of matrix completion? Well, it's a problem of a matrix. So there is a matrix W, but I'm not going to give it to you. I'm actually going to give you entries, okay? And then you have to give me the other entries. That makes sense? So what I claim is that, in fact, you can view matrix completion as a very special case of this, or if you want, a very special case of multitask learning for a specific choice of the input space. Or if you want, in this setting is to discover which input space we need to use, the question is, how should I choose these measurements so that here, rather than have x, what I have is wij, okay? Or I guess ji. What is the measurement here that applied to the matrix W will give you the entries ji? So this guy here would give me this. So what is a good choice for the xi? So that what you have here, probably I screwed up the indices here. No, it's fine. So you have to choose, do you see it? That's, at this point I have to say that it's not too hard to see. Eh? So I'm assuming that you're sleeping. So you have to do something like this. So you have to take the orthonormal basis in RT, the orthonormal basis in RD, and then you compose them like this, and this is basically go in and pick that component, okay? So this is the special case where the input point, rather than be RD, okay, is just exactly the elements in RD that are exactly the orthonormal basis of that space, okay? So if you want, this is the problem of matrix learning in the linear case, okay, where you have measurements of this form. And you can view it as a special case of multitask learning, where you take the function space to be linear. And you can, depending on the point of view you take, some problems are more natural than some others, okay? The multitask problem is very natural there. The multivariate regression problem is natural both here and there. The matrix completion problem, I guess, you would be more natural here, or at least I do feel it slightly more natural here. But again, it's just a specific choice. So there is a clear connection between these two kind of problems, and the connection comes from the fact that we restrict, at least for now, we restrict ourselves to linear functions and linear measurements, okay? So on Wednesday, we're going to relax this assumption and ask what happens if you want to relax this to having non-linear function. Use, for example, non-parametric modern and kernels, okay? Does it make sense? So general multitask learning, matrix learning, few connection, 3 problems at least that can be seen as special. Multitask learning, multivariate regression, matrix completion, okay? So how do we do this? So there are a few approaches, okay? I need to tell you 3 more things. It's not late. Well, it's 2:20. So let's first write down the way that, the simplest way to do this, that probably, and let's discover that that's not a good idea. You want to learn this problem. You know that you make the assumption that they're all linear, okay? how can you choose this? The simplest way that is going to turn out to be a bad way. Least squares, you took it here, for example. Okay, fair enough. You took a loss. Take the squared of each component and sum it up. Okay? So let me write it here. So the simplest thing you can think of is choosing R, that in this case is just the R of big W, or if you want the R of W1 T. Okay? And then just take these to be the sum of the norms. Okay? And of course, these I can also write, if you want, like this. Okay? But it's easy to see that this is just the square root of the Frobenius norm. Okay? You just go in and just plug it in the definition. Okay, what's the problem of this choice? That this is completely, so this term, if you try to minimize this over the different components, it decouples. We already noticed back there that the same thing happens for the error. So if you make this choice, you're just in the non-multitask philosophy. Okay, you write down everything with the notation of multitask, and you're just solving each problem separately. Okay. One natural way to go is, well, let's choose a different regularizer. Okay, and now that we're in this world, we can take a matrix regularizer. Now, one way to start to think a bit how to design regularizer is to notice that yet another way of writing this is to write it as, say, the sum of the square of the singular values of the matrix W. So you take W, you write it as U sigma W V transpose. Okay, sigma here is the matrix with the singular values on the diagonal, and then this, it's easy to see that it is just the sum of the square root of the singular values. Okay, so if you allow me to use this notation both as a diagonal matrix and the vector of singular values, this will be just what? Squared norm, the usual, okay, squared norm of the vector of singular values. Okay, so let me do it like this. Now, one thing you can ask is, okay, can I use some other regularizer that will not have this property that you can always rotate things so that they separate, and will some couple the problem? Okay, well, this is the little L2 norm of the singular values. What could you use? Well, another norm on the singular values. Like what? Well, this is L2. The next one over is typically L1. I don't need to put the absolute value here because these are already, they could be positive. And, and the notation for this is this, okay? So you can, this is what is called norm for obvious reason. Sometimes it's called the nuclear norm. Of course, here I don't even mention it. You can take a bunch of other things. Instead of taking the one norm, you can take the p norm, okay? And you can work on those values, okay? And this one doesn't decouple anymore. There is not a trivial way to write it as t separate problems, okay? This is one possibility, okay? Another possibility would be to actually go in and, look at this, where did I, here, okay? And say, why the 2? I could put a 1, okay? So again, you could do something like, say, a 1 norm matrices. Okay? And why 1 norm? Why not a p norm? Sure, you can do the p norm, okay? And again, these are going to be all design choices, okay? You can keep on going. You can do group norms, okay? For example, suppose that I tell you I have t, okay? And I'm now taking for all of them the same features, but I know that only a small number of features is going to be important, and it's going to be that those that are important for everybody. And those that are not important for everybody, okay? And I ask you, design a regularizer that is going to do this. How do you do? How do you design a regularizer that is going to select the same features for all the tasks?
Penalize difference in feature in weights for different tasks.
Here or here? I mean, the keyword here is to think about, if you see, we are kind of going through the whole idea of sparsity for vectors, just viewing it in the case of matrices, either entry-wise or on the singular values, okay? The next step over, if you're running sparsity, was group sparsity. So if you want to kill columns or rows of the matrix, say, I know that certain features are going to have to be 0 for all the tasks. What you can do is that you can group all those features that will correspond to a, or in this case, a column of the matrix. And you basically do a group norm on that, okay? And you keep on going, okay? You can design, depending on the kind of information you have, you can design different regularizers. So we don't want to do that. But the last thing I want to do is just to show you how do you solve this, okay? Because again, luckily, it turned out that in this case, the story is going to repeat, and we're just going to pretty much use the stuff that you use for sparsity. In the entry case, I don't have to tell you anything, okay? The idea is always that what you do is that you write down a proximal problem, okay? So you do something like this. You're going to have some kind of so you're going to the empirical error is just going to depend on the matrix. You're going to take the gradient step, and then you're going to compute the prox of the matrix, okay? In the case of Frobenius, you can do it by hand because it's just a linear series. In the case of the other norm, you have to sweat a little bit more, okay? In the case of this norm, you can do it as an exercise because there's nothing particular new. This is just entries of a vector. You have to go in and make the computation. You can write down, you can do exactly what we did for the L1 norm, okay? So this could be an exercise. In the case of the singular values norm, okay, the trace norm, it's not that obvious because, well, yes, this is the L1 norm of the singular values, but how do you go in and compute the prox that correspond to this? What would be the hope, you think? If the word was nice, how would the prox of this would look like? Well, this is the L1 norm on the singular values. It would be really nice if what we had to do is to just compute the prox of this, sorry, the singular value matrix, and then to apply the L1 prox to the singular values. That would be what we would hope, okay? That somewhat to compute the prox of matrix valued function in the case of spectral norms, what you have to do is to just compute the singular value and then apply, say, the vector of the corresponding norm. And that turns out to be the case. If you use this kind of norm, okay, which is the basic example of spectral norm, what you have is that the prox of, say, the nuclear norm of a matrix W is just compute the singular value, look at the decomposition, look at the singular values, and apply the corresponding norm on the singular values, okay? But what is this? This is just the soft thresholding. This is just a vector, okay? So what you have to do is that if you want to compute, say, the minimizer of a trace norm regularization in multitask, matrix completion, or multivariate regression, you take a gradient, and each step you have to compute an SVD, and then apply soft thresholding on the singular values, okay? Plugging them all together, take another step of the gradient, and keep on going. So this is the one case where the algorithm is a bit more interesting. In the other cases, you can just, so it's for the spectral norm, and you have theorems which are not trivial, are in the notes, that tells you that you have this nice property that the prox of a matrix of a spectral norm can be written as the prox of the singular values on the singular value decomposition. Okay? So and this is the last bit of very simple information I want to give you today. But so maybe we're going to look at this last step on Wednesday. Okay? And I'm done here.